Okay, class. So with this problem, what we're going to do is we're going to model the forces acting on this charged bowling ball here and due to these other charges. And we'll try to answer these questions. So what we have is a charged bowling ball, and we want to know the direction and magnitude of the electric force that acts on this charged bowling ball due to the other charges. And then we want to know, well, what's the direction it's going to go and what's its instantaneous acceleration. Now, I haven't worked out all the numbers, but what we'll do is we'll go through the procedure and get it to a point where we could just calculate the numbers. So the first thing that you want to do with these types of problems is determine what types of forces should you consider and in what directions do they act. So we're going to draw a free body diagram for this bowling ball. And so I'm going to change to a very bright green color so that we can see that. So the first thing is there's an interaction between that charge and that ball. And that interaction is along the line that connects the two, and it points up and to the right. And so that's F1. We know that that's an electric force. Now, there's another interaction between that charge and the bowling ball, and it points up and to the left, and it is oriented such that these two charges are the same size. Therefore, the strength of these two forces, I'm going to call that F2, are the same, but they point in different directions. And if we break that down as vectors, what we will see, I'm going to change the color again here, is that the x components conspire to give us no x component, but the y's give us, whoops, I went off the page here, but they give us a force, electric, that is all in the y direction. Now there's one last force which we're going to consider, and that's the gravitational force that acts on this ball, because we need that for part 2, and that points down. So we're going to call that Fg. Now, the first question is, well, what's the direction and magnitude of the net Coulomb force, the net electric force? Well, the direction we already know. The direction is upward. Oops, let's change to a color that you can actually see. Sorry about that. Black. So the direction is up, and that's because the x components cancel. Now we have to determine the magnitude of that force. So the easy thing to do, I would say, is to determine the magnitude of each of the forces F1 and F2. Now the magnitude of F1 is going to be equal to the magnitude of F2, and then we can do a vector projection. We can figure out how much of that force is in the y direction. So that's K times Q1, which we're going to call that Q1. We'll call this guy Q1 also. And we'll call this one Q2. So that's K Q1 Q2 over the separation squared, and that's the absolute value, just in case there's a positive and negative, but they're both negative in this case. So the magnitude of those forces, F1, F2, and I believe I worked this out at some point, is 9 times 10 to the 9, that's K, times Q1, which is going to be magnitude 0.1 times 10 to the minus 3, times 0.04 times 10 to the minus 3, that's those two charges in coulombs, times the separation. Now we got to deal with that separation, so this is of distance 1 meter, and therefore this distance here is 1 squared plus 2 squared square root, which is the square root of 5. And so r squared here is just going to be 5. And so that magnitude, I believe, as we calculated it in class, so it's the magnitude of F1, it's also the magnitude of F2, I want to say that's like, it's 72-ish newtons, something like that. Point is it's a magnitude, right? And so now we have to say, well, how much of that is in the y direction. And so we have to deal with this angle between the direction of the force and the horizontal. So we're going to call that angle theta. And so to find the actual force, F1, for example, we need to know the magnitude of F1, and we need to know what r hat is. And so r hat is just going to be, in this case, it's going to tell us about the vector projection of the force in the vertical direction when we add them together. So what we're going to have is F2 is its magnitude, and I should change these to R1s and R2s. Right, so these would be the individual forces, but the way that they conspire is to give us only y direction. So what we really care about is what is F1 in the y direction, what is F2 in the y direction, and it's the sum of those two that gives us the net electric force, because that's the only thing that points in the y direction. So what is F1 in the y direction? Well, it's going to be the magnitude of F1 times the, we'll have the sine, because we have the opposite of the angle, and F2 is going to be F2 magnitude sine of that angle, and so we're going to call that theta 1 and theta 2, even though we know that they are the same angle, because the difference, because the distance here is the same, the horizontal distance is the same. Okay? So what is the sine of that angle? Let's do that over here really quickly. So the sine of theta in both cases is equal to the opposite over the hypotenuse. And so the opposite is 2 meters. The hypotenuse is the square root of 5. And so even though we don't know the angle, the angle in degrees, we know what the sine of that angle is just from looking at this triangle. And so in both cases, F1 and F2y, they're both going to be, so F1y and F2y are going to be equal to 72 newtons times the sine of theta, which is 2 over root 5. And so that tells us that the net electric force is equal to twice that. Because both of them contribute in the y direction. So 2 times 72 times 2 over root 5, which I believe is going to be 4 over root 5 times 72. And that'll be in newtons. So that'll be our net electric force, and we already know the direction. It is upward. So what we're left with is answering question 2. And so to answer question 2, what's the direction that the ball will go? That's actually a little bit easier because we can find the gravitational force as we did. So I'm going to change color here to answer question 2 so that you can distinguish between the two. So the gravitational force we need to compute, and that would be equal to m times g, which is going to be equal to 8 kilograms times 9.8 meters per second. And so that's about, I'm going to say that's approximately 80 newtons. And so you can see already that the net electric force is going to be higher because it's 4 over the square root of 5 times 72, which is greater than 80. So the ball is going to move upward. So ball will move up, moves up. And the acceleration with which it does that is equal to the net electric force, so F net E that we would have computed, minus the gravitational force, because they point in opposite directions, divided by the mass of the ball. So really the challenging part of this problem is this first part. That has all the geometry in it. It's the second part that uses some of the ideas from the previous course, but it's not really tough stuff compared to the geometry and the calculations that are necessary to compute the first part.